Okay, this is the beginning of class 2, and we're going to start right off the bat with an Excel exercise. So, suppose you usually buy a venti latte from Starbucks every morning for $4.50. But starting this summer, you plan to switch to a large Dunkin' Donuts coffee, which only costs $2 for a large. So, if you save $2.50 every day and earn 10% on those savings, how much will you have saved in 40 years? And then what if you make your coffee at home every morning instead of buying it? So assume you're spending $0 a day on coffee. How much money will you have saved after 40 years? So why don't you pause the video now and try to work through this Excel exercise on your own. And then once you've given it a try, play the video again and we can go through it together. So here's how we're going to do it. Go to Microsoft Excel, and the first thing we need to do is type out all of the inputs to the spreadsheet. So the inputs are going to be, first of all, we have daily savings of $2.50. We have an interest rate of 10%. And then compounding frequency, we're going to need to know that. Now, it's not actually given in the question, but most savings accounts pay monthly interest, so we'll assume that you're earning monthly interest, which means you're getting monthly compounding. And then we'll look at the 40 years in terms of on a monthly basis, so it's 480 months. So compounding frequency is 12 times per year. It's monthly. And we like to color code our inputs, so I'll make these yellow. And then we need to list all the dates. So starting with July 1st, 08, and then we're looking at this on a monthly basis, so the next date is going to be August 1st, 08. And then we want every month until 40 years later, which is July 1st, 2048. And so we can just drag from here. Excel recognizes that we're looking at a monthly on a monthly basis, so we can just drag down all the way to July 1st. Almost there. July 1st, 2048. And then we're going to need 3 columns for this spreadsheet. The first column is going to be our account balance. So let's suppose that we have a savings account. We put all our coffee savings into a savings account. So we're going to keep track of how much savings we have in this column. And then we're going to earn interest every month on those savings. So we have a column for monthly interest. And then we're going to save some money every month from buying cheaper coffee. So we're going to have a column for monthly savings. And for starters, on July 1st, our account balance is 0 because we haven't saved any money yet. And that's an input. And in the first month, monthly interest is going to be based on how much money we have in the account and on the interest rate. So the formula is going to be the account balance, which is B6, times the interest rate divided by the compounding frequency. So in the first month, we earn $0 interest because we have $0 in our account. And then monthly savings is going to be based on how much money we save each day and how many days are in the month. So it's $2.50 every day times the number of days in the month, and the way we can do that is just subtract August 1st minus July 1st, and Excel automatically calculates the number of days in between. So 31 days in July times $2.50 gives you $77.50 of savings in July. And then moving on to the next month, the account balance at the beginning of each month is going to be the sum of the prior row. So it's the account balance from the prior month plus any interest we earned in the prior month plus any savings we had in the prior month. And that's going to give us our account balance in the beginning of the next month. Now we're assuming that we're just saving the money, we're not spending any money in this account. So we're only adding to the balance. We're not never subtracting from the balance. Now these other two formulas, I should just be able to copy them down. So starting with monthly interest. Oh, I forgot to freeze one of the references. So here we need to freeze both C2, which I already did, which is the interest rate, but we also need to freeze C3, which is the compounding frequency. Now I should be able to copy this down. And it says that we earned 65 cents of interest in August. So that's 1 month's interest at a rate of 10% on an account balance of $77.50. And there you can see the formula. It's the account balance, B7, times the interest rate, C2, divided by the compounding frequency, C3. And here, should just be able to copy this down. And we check the formula. C1, which is the daily savings, times the quantity A8 minus A7, which is September 1st minus August 1st. So August also has 31 days, so this looks right that July and August we have the same amount of savings in both months. And now that I have all these formulas written out, I should just be able to copy them down all the way for 40 years to July 1st, 2048. Let's scroll down and see. Actually, I'll freeze the cells up here so we can still see what our column headings are. So the way to do that is you go to Window, Freeze Panes, and now when I scroll down, you can still see the column headings. So we scroll all the way down to July 1st, 2048, and we see at the end of 40 years, we will have accumulated $481,265.69. So simply by saving $2.50 every day and putting it away and earning interest, earning a return on those savings, $2.50 a day turns into almost $500,000 at the end of 40 years. So it just shows, this is just another example of the power of savings and the power of compound interest. Now the second part of the question, what if you make your coffee at home every morning instead of buying it? So for this, we'll just assume that it doesn't cost any money to make your coffee at home. Of course, in reality, you'll have to buy the coffee grounds or the coffee beans, and there'll be a little electricity for to run the coffee machine, but all those costs are fairly negligible. So for simplicity, we will assume that it costs $0 every day to make your coffee, which means that you're actually saving $4.50 compared to buying at Starbucks. So all we have to do is just change this one input. all the values in the spreadsheet will update, and then we scroll down to the bottom, and we see that at the end of 40 years, we will have accumulated $866,278.24 worth of savings. So, again, we can accumulate just phenomenal amounts of money by making prudent decisions about saving a little bit of money every day and putting it away and earning a return on that money. And decades down the road, that small amount of money every day turns into a lot of money. So that's it for this Excel exercise. Now, there's another reason that we were looking at this example, aside from just showing the power of savings, and that's because we're going to use it to learn a new formula, some more financial math. So what we're going to do is examine the coffee example in more detail. First, we're going to make a simplifying assumption that our monthly savings are $75 every month. So if we go back to the spreadsheet here, when we had $2.50 of savings every day, our monthly savings were anywhere between $70 and $78. We take the average real quick. So we averaged about $76 of savings every month. But it was a little, depending on how many days per month, the amount of savings changed. So we're making a simplifying assumption that it's just 75 bucks a month of savings. So after 1 month, we've got $75, which is just the money we save. After 2 months, we've got this number in yellow here is that $75 that we started with, and then we will have also earned some interest on that $75 that we had at the end of month 1, and we will have saved an additional $75 during month 2. After 3 months, this nut quantity in yellow here is the same as the line above. That's how much money we had at the end of 2 months. And we're going to earn some interest on that money that we had at the end of 2 months. And plus, we're going to save an additional $75. So don't worry, we're going somewhere with this. Now, what we can do is we can multiply through by this quantity 1 plus 10% divided by 12. So we multiply through, and we get 75 times the quantity 1 plus 10% divided by 12 squared, because we're multiplying this quantity times this quantity, so it just becomes the quantity squared. And then we also get 75 times that quantity, so that's this times this. And then we have this $75 of savings at the end, as we did before. So all we did from this line to the next line is we just multiplied through by this quantity. So we started to simplify the expression. And then here, just to take up a little less room and also to generalize the formula, we're replacing these numbers with symbols. So the $75 of savings that we have every month, we're going to replace that with PMT, which stands for payment. So we're basically, our savings account is receiving a payment of $75 every month. And then the 10% is the interest rate. We replace that with R. The 12 is the compounding frequency. We replace that with N. And the same thing along down the line. So after 4 months, we're just going to keep going here. So we've got this quantity in yellow is identical to the line above. That's the money we had after 3 months. We're going to earn some interest on that money, which is represented by this, multiplying it by this quantity. And then we're going to have 1 additional month worth of savings. So this is the savings that the money that we save in month 4 is here. And this is all the money we'd saved before times 1 plus the interest rate divided by compounding frequency. So this is how much money we have after 4 months. Now again, we're just going to simplify and multiply through by this quantity. So we're going to multiply this times this term, and what we get is the quantity raised to the third power instead of the quantity squared. Here we multiply these two, and we get 1 plus r over n squared, because here it was just to the first power. And then here we just multiply times the payment, so we end up with this quantity to the first power. And then we stick in at the end our savings, the money that we saved in that month, this final term. Now on this line, all we did is we reversed the order so that the exponents are now in ascending order. So we've got this payment is now at the beginning here, and then we've got the quantity raised to the first power, the second power, and the third power. So we just reverse the order from this line to this line. Now we're running out of room here, so we'll go on to the next slide. This is the same thing from the last slide, just copied over onto a blank slide. And what we're going to do now is generalize it even further, because we've detected a pattern here. We see that after m months, we end up with a series of terms, and in the last one, the exponent is m minus 1. So after 3 months, the last exponent was 2. After 4 months, the last exponent was 3. After m months, the last exponent is m minus 1. And this can be rewritten as a summation. It's the sum of the payment times the quantity 1 plus r over n raised to the k, where k goes from 0 to m minus 1. And this is a little bit awkward to look at, so I've also kind of drawn it out here. So it's the summation of the payment times 1 plus r over n raised to the k, where k goes from 0 to m minus 1. Make that a little bigger in case you can't see it. That looks nice and big. Okay. Now the final step requires a little bit of a leap of faith, which we are not going to prove right now, but basically this summation can be rewritten as a single formula, specifically this formula right here, which is the payment times the quantity 1 minus the quantity 1 plus r over n raised to the mth power, and that's all divided by the quantity 1 minus the quantity 1 plus r over n. So again, that's really awkward to look at, so we've got it right here. Make it a little bigger if I can. So this summation, I'll go back to so this summation, which is the same as this left side of the equation, we're saying that this is equal to this formula. So if we're looking at 480 months, rather than having to write out 480 terms of a summation, we can solve it all with just one little formula, which is this. And again, we're not going to prove it. You just have to take it on faith for now that that this equation is true. So copy this down. And we'll go back here. So let's try to rework the coffee example using this new formula. So we're supposing that you save $75 a month by buying Dunkin' Donuts coffee instead of Starbucks, and you're still earning 10% on your savings. So again, the question, how much money will you have saved in 40 years, which is 480 months later? So all we're going to do is plug in these values to the equation we just saw. So the payment is $75 per month. The rate is 10%. Compounding frequency is 12, and it's for 480 months. So K goes from 0 to 479. But rather than writing out all these terms in a summation, we can just plug them into this formula. We can plug the values into this formula. So the payment is $75 a month. The rate is 10%. Compounding frequency is 12. M is 480 months. And then plug in the rate and the compounding frequency here as well. So there are the values plugged into the summation. And here are the values plugged into this formula. So we plug those in, put it in our calculator. What we come up with is we will have saved $474,305.97. Now if we compare that to the spreadsheet answer, it was $481,265.69. So this is a little lower, but that kind of makes sense because we were assuming $75 of savings per month, whereas in the spreadsheet we were averaging $76 of savings per month. So hopefully this builds some confidence in you that this formula is true and that it works correctly. And so this is great. So this means that rather than having to build a spreadsheet with 480 lines in it, or writing out a summation with 480 terms, we can plug a few numbers into a calculator and come up with the right answer. Of course, this formula requires that the savings be constant. So if this number was changing every month, then we wouldn't be able to use it. Or we would only be able to use the formula to approximate the correct answer. So it has its limitations, but very useful nonetheless. So here is another example. Suppose that you buy 5 pairs of blue jeans every year, and assume that a pair of designer blue jeans costs $150, whereas a pair of Old Navy blue jeans costs $30. So if we decide to buy Old Navy blue jeans rather than the more expensive and fashionable brands, and again we earn 10% on our savings, how much money will you have saved after 40 years? So go ahead and try to answer this question on your own. Again, you're going to use this formula. And I think the only way to do this is look at it on an annual basis rather than a monthly basis. So 5 pairs of blue jeans every year. You are buying cheaper jeans that are $120 cheaper. So 5 times 120 is, I believe, $600 per year. And yeah, go ahead and give it a shot. Pause the video, and when you're ready, we'll go through it together. Okay, so our savings are $120 times 5 per year. The compounding frequency is 1, so there's no denominator here below the interest rate. And then K goes from 0 to 39 because we're looking at a 40-year period. So we plug all those numbers into the formula. It should look like this. This is our annual savings. This is our annual interest rate. Compounding frequency is 1. Number of years is 40. Plug it into our calculator. And we come up with, after 40 years, we will have saved $265,555.53. Follow-up question. Let's suppose that 40 years from now, you take all your savings from buying Old Navy jeans and you use the money to buy designer jeans. How many pairs of designer jeans could you buy? And we'll throw in a little wrinkle. Let's suppose that the price of designer jeans has increased 33% per year over the 40 years due to inflation. So the price of designer jeans has increased somewhat. We're going to try to figure out how many pairs of designer jeans you could buy with all your savings from buying Old Navy jeans after 40 years. So again, pause the video and try to work through this on your own. So the first step here is to figure out how much a pair of designer jeans is going to cost 40 years from now. So if it costs $150 today, and it's increasing 3% every year, then what you would do is you would multiply 150 times 1.03 40 times, because if it increases 3% every year, then you basically need to multiply it by 1.03 40 times, once for every year that passes. So what you come up with is that one pair of designer jeans in 40 years is going to cost $489.31, so quite a bit more than it does today. However, you've saved a lot of money, over $265,000. You divide the amount of savings that you have by the price of each pair of jeans, and we see that you could buy 542 pairs of jeans with that money. And by the way, if you had bought 5 pairs of designer jeans from the start, you would only have 200 pairs of jeans. You would have only bought 200 pairs of jeans. So, and you would have no savings built up at the end. So what we're saying here is that for 40 years, you can buy the cheaper pair of jeans. You still get to wear blue jeans. You're not foregoing blue jeans. You're just wearing less fashionable blue jeans. And then at the end of 40 years, you can buy hundreds and hundreds of the more fashionable jeans with the savings that you accumulated. I mean, this is more than twice as many pairs of designer jeans than you would have if you had been buying them 5 per year for 40 years. Now, of course, nobody would want to buy 540 pairs of blue jeans, but the point is that by saving now and consuming later, you can greatly increase your ability to consume, and it basically dwarfs the amount of consumption that you can do if you just consume a little bit all along. Finally, we are going to finish with another Excel exercise. So let's suppose that you get a credit card. Hooray. Let's suppose that you make $100 worth of purchases on your credit card every month. And rather than repay the full balance at the end of each month, you only make the minimum payment required, which we're going to assume is 1% of your balance every month. So the way that credit cards work is you go to the store, you give them your credit card, you buy something, and you're not paying for it, essentially. The credit card company pays for the purchase, and you're promising to pay the credit card company later. And at the end of the month, you get a bill, and you can pay the credit card company all of the bill, or there's a minimum payment that the credit card company is going to require. If you don't make the minimum payment, they'll cancel your card. But if you at least make the minimum payment, then you can use your credit card again next month. Now the catch is that credit card companies charge a lot of interest on the the balance that you don't repay. So in this example, we're going to assume the credit card company charges 20% interest on your credit card balance, which is not at all unusual for a credit card. A 20% interest rate is it's very high, but that's what credit card companies charge. Um, so any money that you don't repay at the end of the month is going to be subject to a 20% interest rate. And if you do repay your money at the end of the month, then you don't get charged any interest. So now, by the way, this 20% interest rate, it may sound egregious and unfair, but from the company's point of view, they are agreeing to lend you money without really knowing anything about you and just trust that you're going to pay them back. So they're taking a lot of risk, but they're hoping that they have enough customers who are trustworthy and who are financially stable, that they're going to end up making money at the end of the day. But certainly a lot of people build up too much credit card debt and they fail to pay it back, and on those people, credit card companies lose money. So 20% interest is high, but they're taking a lot of risk, so it's warranted. Anyways, the question is, how much money will you owe the credit card company after 10 years or 120 months? So just to recap, you're making $100 of purchases every month, and rather than repay the $100 every month, you're just going to pay the minimum payment, which is 1% of your total balance. And then you're going to accrue 20% interest on that balance every month. For 10 years, how much money are you going to owe at the end? So again, pause the video, go ahead and try to create a spreadsheet that answers the question. And once you've tried to create your own spreadsheet, you can hit play and we'll go through how to do this together. Okay, so again, we're going to start by typing in the inputs to the spreadsheet. So we're going to have monthly purchases, or spending, we'll call it, monthly spending, $100. We're going to have an interest rate, which is 20%. Compounding frequency, again, it's going to be 12 because they charge interest on a monthly basis. You get your bill on a monthly basis, and then every month you're charged interest. And the minimum payment we said is 1% of your balance. And I think that's it. So again, we'll color code these in yellow. And we'll list the dates. Starting with July 1st. We're looking at this on a monthly basis. And we're looking 10 years into the future. So July 1st, I went too far. July 1st, 2018 is the end date. Okay, and we're going to have several columns. For starters, we're going to have our start of month balance. So this is how much money we owe at the start of each month. And we are going to have interest on that balance. This is interest expense, whereas in the past we've been looking at interest income because it's in the past we've been looking at money that you've saved and interest that you earn on those savings. Here we're looking at money that you owe somebody, and so it's an interest expense. We're going to have monthly spending. And then that's going to lead us to our end of month balance. And then finally, at the end of every month, we're going to make a small payment. So again, for starters, our start of month balance is 0, so we haven't spent any money yet, and that's an input. And then the formula for our interest is going to be our monthly balance times the interest rate, which is 20%, divided by the compounding frequency, which is 12. And in the first month, we don't accrue any interest because we haven't used the credit card yet. Our monthly spending is just going to be fixed at $100 we set every month. And then our end of month balance is going to be whatever our start of month balance was, plus any interest that we've accrued during the month, plus any spending that we've done during the month. So at the end of the first month, we spent $100, and that's our balance. And then our monthly payment, we said, is going to be 1% of our balance. So the first month is going to be $1. And then going to the next month, at the start of the month, we're going to have a balance equal to the prior month's end of month balance minus whatever we paid down. So at the end of July, we had a $100 balance. We made a $1 payment, so at the beginning of August, we have a $99 balance. And now we should be able to copy the rest of these formulas down, starting with interest. Our interest in August is going to be $99, B8, times the interest rate, which is 20%, C2, divided by the compounding frequency, which is 12, C3. And we see that in August, we are going to accrue interest of $1.65. Our monthly spending is fixed at 100, which is C1. And then our end of month balance is whatever we had at the start of the month, which is $99. Whatever we owed at the start of the month, rather, which was $99, plus any interest expense we've accrued, which is $1.65, plus any spending we've done that month. So our end of month balance in August is $200.65. And then our monthly payment is 1% of that. $200.65 times 1% is about $2.01. So now we should just be able to copy all these formulas down for 10 years. And again, we'll freeze the cells. You go to Window, Freeze Panes. And this way we can scroll down and still see the column headings. So after 10 years' time, we're spending $100 a month. We will owe $17,910.97. So point being, it's really easy to build up a phenomenal amount of credit card debt. One, because credit card companies will generally let you keep spending as long as you're making the minimum payment. But two, because they're charging a 20% interest rate, and that's gonna add quite a bit to your credit card debt very quickly. If we take a look here, in July of 2018, we're still spending $100 a month on purchases, but our interest costs are 3 times that amount, almost $300 of interest expenses every month that are adding to our credit card debt. And also, if we look over here, we're paying down almost $200 of our balance every month and we're only spending $100 every month. So um, the point is, before long, your credit card expenses are much greater than merely the purchases you make, because your debt gets so big and you have to pay down even 1% of your balance is a huge amount, and the interest just keeps on accumulating, and it gets to be completely oppressive. So the moral of the story is, pay your credit card debt at the end of every month religiously, because if you pay at the end of the month, you don't get charged any interest, and credit cards become a very convenient and harmless tool for making purchases. Whereas if you allow yourself to accumulate debt on your credit card, they become a very harmful thing. Um, so that basically covers it for this class. We went through a lot of things really quickly, so feel free to just watch this again, and hopefully it'll make more sense the second time if it didn't make sense the first time. And then when you're ready, you can move on to watching class number 3.